Okay, what we're going to look at now is a very particular base called the natural base, and we usually see it as the letter E. So this letter E represents an irrational real number, so kind of like pi is 3.14 dot dot dot. It's not a fraction in any way. So E is this number 2.718281 dot dot dot. It's pretty much stored in your calculator for any calculations that you might need it for. So you don't need to like know this number, just like you don't need to know pi past 2 decimals. I sure don't. So yeah, just while practicing getting used to this E, we can do a couple of applications at the same time of typical things that are expressed as exponentials and often expressed with a base of E. Yeah, just before I get into that, it might be a little bit annoying to you that all of a sudden there's this letter that's going to get used really frequently for the base of a lot of your exponential functions. If you do plan on taking calculus, so it'll sort of be explained why you use E. Everything that you do with calculus, if you use E instead of a base of like 2 or 5 or 10 or nice numbers, it actually works much better. Everything works better with E. It's all simpler with E. So we learn it because it's better in calculus, basically. Yeah, so we're given this formula for the value of an investment after T years, and it's A of T. So that A typically stands for annuity, the value of an annuity. So a thing that gets more value over the years. And then we have this 12,000 e to the 0.025t. So first of all, we'll find the initial value. So initial just always means t equals 0. And so the initial value will be A of 0 equals 12,000 e to the 0.025 times 0. That's just e to the 0, which is 1. And so the initial value is actually just 12,000. We'll talk a lot more about some applications later on, and this is a very common formula for some of these applications. So we'll talk a little bit more about how we can construct this from a given set of information. But yeah, it corresponds with that number out front, the 12,000. And yeah, so find the value after 6 years. So there's not too much to this. We can't do much equation solving yet, but this just means t is 6. Plug it in. A of 6 is 12,000 e to the 0.025 times 6, which is 12,000. That should be e to the 0.15. And so I'll just go over how you're probably going to evaluate that on your calculator. So I can't do that in my head at all, certainly because e is this really crazy ugly number. So what you might want to punch in your calculator is the number 12,000. I'm assuming you have a scientific calculator with a dual display, and that allows you to just like type out a line of math and hit equals. So you'll hit 12,000. And so most of your calculators are going to require you to use some kind of like shift button. Or it might be labeled as like second to hit the secondary options. And so there's not really usually an E button. So typically the button that you're looking for is this one that says LN. And then often you'll see in the top left corner, or like somewhere above it, there'll be this little e to the x to indicate that we want that function. So the shift is what takes us to those secondary functions that are usually written just above the button. So I'll hit 12e, and then this gives me my e to the power of. I'll type in my 0.15, and then if I hit my equals, that should be how we punch this in. E to the 0.15. Yeah, and yeah, then I'll get equals. Notice I didn't have to write times because the calculator, just like the way we write this out, will assume that if I don't write anything between two different objects, it's multiplication. So I get a 13,942.01. And so again, I should put units on this. It's an application. It's not 13,000 puppies, it's $13,000. So that would be the answer. So after 6 years, you get a little bit more money, right? That's interest accumulating, so it's almost $2,000 in interest. So we'll look at another really common example using exponentials. Okay, so a second application is going to be a population of a bacteria. Actually, pretty much all populations can be modeled by something fairly similar to this. So this equation that you can see here is actually, it's called a logistic equation. There's a little bit of two different exponential parts to it. If you ever go far enough with math to see differential equations, you'll see the reasoning behind this formula here. So we've got the population of bacteria in a petri dish after T hours can be found by this P of T formula. So our initial population, just as before, that's going to be P of 0. So we'll get 1,000. E to the 0 is just 1 over 3 plus 2 e to the 0. So that would be, 10,000, not 1,000. 1,000 over 5, which should be 2,000. So it is starting with 2,000 bacteria at the very start. And so let's say we find the population after 4 hours. So we'll just plug in 4. It's going to be some number crunching here. 10,000 e to the, I'm going to plug it in and actually just simplify this as I go. So that'll be e to the 0.12 over 3 plus 2e to the 0.12. I don't want to have to do this huge calculation in my calculator, so I'm going to reduce the top. Now I'm going to carry a bunch of extra decimals here. So that's about 11274, let's say 0.97. And the bottom, I'm going to clean that one up to e to the 0.12 plus 3 is about 5.255. I might actually carry a few more in here. I should probably try to carry roughly the same number of digits here, but it's not going to be perfect. Let's say, actually, 5 is actually pretty good looking at this number. So a little trick I can do on my calculator, since I did the denominator first, you usually have like a little power of -1 button. I can actually hit that, and it sort of puts it on the bottom, and then I can multiply by the top. But no matter how you get it, we should be getting 214. I'm going to round it up because it's a bacteria. I shouldn't really have any decimals in the answer. You can't really have half a bacteria. So we get this growth. It's actually not particularly fast growth here, 2,146. So I kind of just pulled these numbers out of a hat. So sometimes I give these examples and the growth is astronomical immediately. But yeah, so after 4 hours, it's not a crazy amount of new bacteria. And so we're going to do 10 days. We do need to make sure we put this into hours. So 10 times 24 is 240 hours, right? T is an hour, so I have to be consistent with that. So P of 240 is going to be 10,000. And I'm going to simplify the 240 times 0.03, so that'll be e to the 7.2. Divided by 3 plus 2e to the 7.2. I'm going to just do this in one go in my calculator, so I just make sure you're careful with brackets, like in dividing the bottom. It's probably good practice for you to try to get this in there in one go. So I'm going to put the whole bottom in brackets when I plug this in my calculator. And so what I'm actually getting here is about 4,994. And so it's pretty close to 5,000. Actually, some things that you'll see with this logistic equation, what that number basically as t goes on and on and on, these two exponentials, because we know they kind of both shoot upwards, right? They get so big that as t gets bigger and bigger, really that 3 stops having any weight in the equation. And you basically just get this 10,000 e to the whatever over 2 e to the same thing. And so ultimately, as t grows and grows and grows, it starts getting a lot closer to this number here. So what we end up getting for this curve, and again, I don't expect you to be able to reproduce this, but just to see what's happening and why this is relevant, a typical exponential curve looks like, I'm going to draw it in blue, something like this. So we know that a lot of populations, if kind of left to grow uninhibited, they would just explode really fast. Like if you put 10 rabbits in a huge open field, that population is going to just keep growing and growing and growing. But at some point, that field is only so big. And so at some point, you can't have more rabbits. More rabbits can't survive in the field. Like there's only so much grass or carrots for them to eat or whatever rabbits eat, and there's only so many resources for the rabbits. So at some point, their population actually has to start leveling out. And that's what the logistic model does. It looks like exponential at start when there's not really anything keeping the population down, so when it grows really, really fast. And then gradually factors come into play that start slowing the growth down. So even in the real world, bacteria and virus spread are going to follow a similar model. At first, they're just going to go get everybody sick. But then as more and more people get sick, things start slowing the growth down. And various other factors start slowing the growth down. If we're assuming there's nothing like better treatments or cures, it will actually just start slowing itself down. Also because there's less people available to actually get sick at some point. So almost everything with growth has what you'd actually call logistic growth, like this. So it's a pretty important function in the real world.